Так, ну что, осталось проверить, как это работает. Здравствуйте. Сейчас попробуем проверить. Так, в эфире. Чего? Ага. Супер, кажется, работает. Супер, кажется, работает. Поразительно. Никак не ожидал, что оно заработает. Okay, so at the previous lecture we discussed the Rich-Schauder theory. So let's recall that this theory deals with operators with compact perturbations of the identity operator on the Banach space. That is, it deals with operators of the following form: the identity operator on the Banach space plus some compact operator. And the main point of the Rich-Schauder theory is that each such operator is Fredholm, and the index of this operator is 0. This is the main statement of the Rich-Schauder theory. And also we have a rather useful result, the so-called Riesz decomposition for such operators. First of all, each operator of this form has finite ascent and finite descent, which means that there is a non-negative integer p such that if we denote by kp the kernel of t to the power p, then this is equal to kp plus j for each non-negative j. And the same is true for the images. So the image of t to the power p is equal to the image of t to the power p plus j. In other words, the chains of the kernels and of the images of the powers of t stabilize. And if we choose such a number p, we have the following Riesz decomposition. Namely, the space X on which the operator acts can be decomposed into the direct sum of Kp plus Ip. They are both closed and T-invariant, closed T-invariant subspaces. So the operator T becomes kind of direct sum of two blocks. The restriction of t to the first summoned is nilpotent. And the restriction of t to the second summoned is a topological isomorphism, or ultimately is invertible. So this is an nilpotent part, and this is an invertible part. So this is the structure of our operator. Okay, so today our first goal will be to apply the Riesz-Schauder theory to the structure of the spectrum of a compact operator. First of all, let's recall the definition of the spectrum of a bounded linear operator. So suppose that X is a Banach space over the complex numbers. So when we study the spectrum, we always assume that we work over the complex numbers. And let's recall that the spectrum of a bounded linear operator, so we assume that T is a bounded linear operator on X. The spectrum of T is the set sigma of T, which consists of those complex numbers lambda, such that T minus lambda 1 is not invertible. Is not invertible. By invertible, I mean the invertibility in the algebra of bounded linear operators. But by the open mapping theorem, by the, or more exactly by the inverse mapping theorem, due to Banach, not invertible is equivalent to is not bijective. Because each bijective bounded linear operator is automatically a topological isomorphism. So it is an invertible element of this algebra. So this is the spectrum of our operator. We know that it is always compact and non-empty. And let's also recall the definition of the point spectrum. The point spectrum of T is just the set of all eigenvalues. It is denoted by sigma p of T, and it consists of those lambda, such that those complex numbers lambda for which the kernel of T minus lambda is non-trivial. So, in other words, this means that lambda is an eigenvalue of T. And clearly the point spectrum is contained in the spectrum. If this kernel is non-trivial, then of course the operator is not invertible. But in general, this is a proper subset. So of course, if X is finite dimensional, then we know that each lambda, we know that each non-invertible operator has non-trivial kernel. So in the finite dimensional case, the spectrum and the point spectrum are the same. But in the general case, the point spectrum can be strictly smaller than the spectrum. Okay, now we have the following result about the structure of the spectrum of a compact operator. This is our theorem 1. So suppose that X is a Banach space, and suppose that T is a compact operator on X. Then I claim that, first of all, if we take a non-zero point in the spectrum, lambda is a non-zero number in the spectrum, then actually lambda is an eigenvalue of finite multiplicity. So lambda belongs to the point spectrum, and lambda has finite multiplicity. Which means that the dimension of the respective eigenspace, that is, of the kernel of T minus lambda, is finite. And moreover, lambda is an isolated point of the spectrum. Lambda is an isolated point of the spectrum. So each non-zero point in the spectrum is isolated and is an eigenvalue of finite multiplicity. And second, which is just a simple corollary of 1, the spectrum is at most countable. The spectrum is at most countable. So by looking at this result, we see that actually we have only two possibilities. Either the spectrum is finite, or the spectrum is countable, and can be arranged into a sequence which converges to 0. It necessarily converges to 0 because each non-zero point is isolated. Well, let's now prove this result. So we take a non-zero point lambda in the spectrum, and we observe that the operator t minus lambda can be written in the following form. And the expression is in brackets is an operator of the form the identity operator plus a compact perturbation. So this operator belongs to 1 plus q of x. So this observation implies that the Richauder theory applies to t minus lambda. So it is of the form 1 plus a compact operator modulo this scalar multiple. Okay, now in particular we see that t minus lambda is a Fredholm operator of index 0. And the Fredholm alternative implies that the kernel of this operator is non-trivial. So it is a Fredholm operator of index 0, and it is not invertible. In this case, the operator cannot be injective. So the kernel is non-trivial. And moreover, the dimension of the kernel is finite, because the operator is Fredholm. So in particular, we see that lambda is in the point spectrum. Kernel is non-trivial means that lambda belongs to the point spectrum. Now we have to show that lambda is an isolated point of the spectrum. Why is it isolated? Let's apply the Riesz decomposition. So we know from the previous lecture that there is a non-negative integer p such that x becomes the direct sum of kp plus ip, where kp is the kernel of t, not t, but t minus lambda. Now we apply everything to t minus lambda. So kp is the kernel of t minus lambda to the power p, ip is the image. And both kp and ip are closed. Kp and ip are closed and t invariant. Moreover, kp is finite dimensional because the operator is Fredholm, and so each power of this operator is also Fredholm. Kp is finite dimensional. And finally, it is non-trivial. It is non-trivial already because this one is non-trivial. Okay, what can we say about the spectrum of such an operator? So since we have this decomposition, and both the summands are invariant, this readily implies that the spectrum of T is the union of the spectra of the restrictions. So the spectrum of T is the spectrum of T restricted to Kp, the union of this part and the union and of the second part, that is, of the restriction of T to Ip. This follows from this decomposition, and this is more or less immediate. So since both subspaces are invariant, it's obvious that an operator on X is invertible if and only if an operator for which both summands are invariant is invertible if and only if the restrictions to each of the summands, both the restrictions are invertible. So it is not invertible if and only if at least one of the summands is not invertible. And so we have this formula. Okay, now what can we say about, for example, the first subset here, the restriction of T to Kp? Well, we know that the restriction of T minus lambda to Kp is nilpotent. And the spectrum of a nilpotent operator is 0. The spectrum of each nilpotent operator is 0. In other words, this means that the spectrum of T restricted to Kp is just lambda. Okay, now what can we say about the second set here, the restriction of T to Ip? Well, also we know that the restriction of T minus lambda to Ip is invertible. Is invertible. In other words, this means that 0 is not in the spectrum of this operator. 0 is not in the spectrum of this operator, T minus lambda restricted to Ip. Or equivalently, this means that lambda is not in the spectrum of T restricted to Ip. If we now look at this formula again, let's denote it, say, by star, we see that this formula becomes the following one. The spectrum of T is the disjoint union of lambda, this is the first part of the spectrum, and the spectrum of T restricted to Ip. So, in general, we know nothing about the second part, but we know that lambda is not in this spectrum, so we have the disjoint union. Now, let's recall that the spectrum of each operator is compact. So, in particular, this one is compact. In particular, we see that it is closed in the spectrum of T. So the spectrum becomes a disjoint union of lambda and a closed set. So since the union is disjoint, this means that this point lambda is, well, it's relatively open in the spectrum. Or equivalently, this is an isolated point. Lambda is an isolated point of sigma of T. And this completes the proof of part 1. So we have shown that lambda is isolated in the spectrum and it is an eigenvalue of finite multiplicity. Now the second part becomes a simple corollary of part 1. Namely, let's take a natural number n, and let's denote by Kn the intersection of the spectrum with the following set. So what can I say about Kn? First of all, it's a compact set. Kn is compact because it's a closed subset of the spectrum. And since we know that all non-zero points in the spectrum are isolated, we see that all points of Kn are isolated. Is compact, and all points of Kn are isolated. This can happen if and only if Kn is finite. Well, Kn is finite, and if we now take the union of all the Kn's, we get the spectrum minus 0. So sigma of t minus 0 is nothing but the union of all the Kn's. And so since each Kn is finite, we conclude that this union is at most countable. And this completes the proof. Well, in the general case, that is in the case where we have a compact operator acting on an arbitrary bounded space, this result gives us more or less all the information about the spectrum. So our next goal is to look at the special case where our operator is not just compact, but is when it acts on a Hilbert space and is self-adjoint. It turns out that in this case, we can refine this result and obtain more information about the operator. So our next goal is to discuss compact self-adjoint operators on the Hilbert space. The central result here will be the Hilbert-Schmidt theorem. I formulated this result at the end of the previous term, but I didn't prove it. So now we will give a proof, and the proof will be based on the Ritschauder theory. So it's different from the original approach by Hilbert and Schmidt, who worked actually not with operators, but with bilinear forms. But our approach is definitely shorter than the original approach by Hilbert and Schmidt. First of all, so let's recall first of all let's recall the definition of an adjoint operator for an operator between Hilbert spaces. So we'll suppose that H is a Hilbert space, and let's recall that we have the Riesz representation theorem, which gives us a bijection. There is an antilinear isometric bijection. That's denoted by R. R is for Riesz. So it's an antilinear isometric bijection between H and the dual space H star, which takes each vector little x in our space to the following linear functional on x star, on H. So this is just the inner product with x. So this is the Riesz representation theorem. And let's now suppose that we have two Hilbert spaces, H1 and H2, and a bounded linear operator from H1 to H2. H1 and H2 are Hilbert spaces, and T is a bounded linear operator from H1 to H2. And we can draw the following picture. So this is H1, this is let's start with H2. This is H2, this is H1. Here we have the dual spaces, H2 star and H1 star. And we have the dual operator, T star, from H2 star to H1 star. And now let's compose it with these two canonical bijections, R2 and R1, which are defined by this formula. And since they are bijections, we can start here and go here, here, and then down here. And we get a map T plus from H2 to H1, which makes the diagonal commute. And this map, T plus, which is explicitly given by the following formula, is called the adjoint of T. In Russian, сопряженный оператор. It's more or less immediate from the definition that this operator T plus is a bounded linear operator from H2 to H1, and the norm of this operator is equal to the norm of T. Simply because this is true for T star, and because R2 and R1 are antilinear isometric bijections. So we will follow the standard convention and denote T plus by T star. Of course, this is an abuse of notation, but usually this doesn't lead to any problems. Because when we work with operators between Hilbert spaces, normally there is no need to consider dual spaces and dual operators. So it's a standard convention that if T acts between Hilbert spaces, then T star, by default, T star denotes not the dual operator, this one, but rather the adjoint operator. Let's recall some simple properties of adjoint operators. First of all, position 1, T star is a unique map from H2 to H1, satisfying the following identity. So it is uniquely determined by the following formula. The inner product of Tx and y equals the inner product of x and T plus of y for all x in H1 and y in H2. So this is a useful characterization of adjoint operators, which doesn't involve dual spaces. Or equivalently, we can write this in the following form. Equivalently, the inner product of T plus and y, T plus of y and x is equal to the inner product of y and T of x. Oh, well, since we have already adopted this convention, I write T star here. T star. So this identity is equivalent to this one, because this one is just the complex conjugate of this one. This is the complex conjugate of this, and this one is the complex conjugate of this. The proof is a simple exercise. This is almost immediate from the definition. You just take this composition given by this diagram and check that this map satisfies these properties. So we get an operation star which takes each operator between h1 to h2 and h2 to its adjoint. In particular, an important special case is the case where h1 equals h2. So in this case, T and T star act on the same space H. So this operation, the operation of taking the adjoint, has the following properties. This is what proposition 2. First of all, it is an involution in the sense that T double star equals T for each bounded linear operator T. So this is very easy. The easiest way of seeing this is just to use the uniqueness here. So if we replace here T by T double star, then we get obviously then the result is true, but since such an operator is unique, we conclude that T double star equals T. Second, the operation of taking the adjoint is antilinear. So if we take a linear combination of two operators, S and T, lambda T plus mu S, it's better lambda T plus lambda S plus mu T, for obvious alphabetical reasons. So this is lambda bar, lambda complex conjugate S star plus mu bar T star. Here lambda and mu are complex numbers, and S and T are linear operators from H1 to H2. Well, indeed, if we take the dual operators, not the adjoint operators, but the dual operators, then this operation of taking the dual is linear. But the adjoint operator and the dual operator are, strictly speaking, they are different. And since R1 and R2 are antilinear, they are not linear, they are antilinear. This implies that we have to take the complex conjugation here. Another more or less obvious property is that if you have two composable operators, S and T, then the adjoint of their composition is T equal to T star S star. So here T acts from H1 to H2, and S acts from H2 to H3. Also, this readily follows from the similar property of dual operators. Property 4, the norm of T star is equal to the norm of T. Here I just repeat our earlier observation. And another very useful formula is the so-called C star property. C star property. So the formula says that the norm of T star T equals the norm of T squared. Well, this is not entirely obvious. I mean, the C star property is not entirely obvious, but it is quite easy. Well, we have proved this formula at the end of the previous term, so probably, well, on the other hand, this is just a minute. The proof was very short, so let me repeat the proof, because we will use this result several times today, and probably not only today. So let's prove the C star property. This is property 5. Well, first of all, the one-way inequality is obvious because the norm of the product is less than or equal to the product of the norms. And the norm of T star equals the norm of T. So we have this inequality. And to get the opposite inequality, we just write the definition of the norm. This is the supremum over the unit ball of the norm of T squared. And the square of the norm of T of x is just the inner product of T of x by itself. Now we use proposition 1. We use this formula. So we take t from here, move it from here to here, and it becomes t star. T star t of x in a product with x. And by the Cauchy-Bonnikovsky-Schwarz inequality, this is less than or equal to the supremum of the norm of this element by the norm of x. But the norm of x is 1, and the supremum of this expression is nothing but the norm of t star t. And so we get the opposite inequality. So the C-star property is very important and is very useful. Actually, it naturally leads to the notion of a C-star algebra, which is probably one of the most important notions in modern functional analysis. We'll discuss C-star algebras at the end of our course, and we will apply them to the proof of the spectral theorem for normal operators on a Hilbert space. Okay, another simple property of the operation of the star operation. This will be proposition 3. For each bounded linear operator between Hilbert spaces H1 and H2, we have the following formulas. First of all, the kernel of the dual of the adjoint operator is equal to the orthogonal complement of the image of T. Second, the closure of the image of T is the orthogonal complement of the kernel of T star. And finally, we have the following direct sum decomposition. H2 is the orthogonal direct sum of the closure of the image of T and the kernel of T star. So this is the orthogonal direct sum, which means that the summands are orthogonal to each other. Well, the proof is a simple exercise for you. Actually, it suffices to prove formula 1, because 2 follows from 1 by taking the orthogonal complements. If we take the orthogonal complements in 1, and if we recall that the double orthogonal complement of a vector subspace is just the closure, then we get 2. So 2 follows from 1, and 3 follows from 2 and from the orthogonal complement theorem. So everything follows from 1, and to prove 1, we may either use a similar result about dual operators. We have the same formula for dual operators, but the difference is that this sign, this symbol means the annihilator. And then recall that the canonical bijection, the canonical Rees bijection takes orthogonal complements to annihilators. Or equivalently, we can prove 1 directly without any dual operators, just by definition. This is very easy. Okay, let's now turn to self-adjoint operators. So from now on, we suppose that H is a Hilbert space. So we will consider operators on H, operators from H to itself. And we say that a bounded linear operator T on H is a self-adjoint. Some people say Hermitian. Well, the name is self-explanatory. Self-adjoint means that it is adjoint to itself. T star equals T. A more general class of operators, but also important, consists of the so-called normal operators. So we see that we say that T is normal if T commutes with T star. Well, it's clear that each self-adjoint operator is normal, but it's very easy to produce examples of normal operators which are not self-adjoint. For example, you can take the identity operator and multiply it by I, by the imaginary unit. It will be normal, but it is not self-adjoint. Okay. Let's observe, first of all, let's observe that T is self-adjoint if and only we have the following identity. The inner product of Tx and y equals the inner product of x and Ty for all x and y in our space H. This is just a special case of our proposition 1. So this formula means precisely that T equals T star. And this observation readily implies the following proposition. This is proposition 4. Proposition 4. If T is a self-adjoint operator on H, and if H0 is a closed T-invariant subspace, then the restriction of T to H0 is also self-adjoint on H0. And this is clear because, well, if this formula holds everywhere on H, then of course it holds everywhere on H0. So the restriction of a self-adjoint operator to an invariant subspace is also self-adjoint. By the way, a natural question, well, is it true for normal operators? This is an exercise for you. If T is normal, then is it true that the restriction of T to H0 is also normal? Okay, so let's now prove some general properties of self-adjoint and normal operators. First of all, we have the following result about the spectrum of a self-adjoint operator. If T is a self-adjoint operator on the Hilbert space, then the spectrum of T is real. The spectrum of a self-adjoint operator is real. By the way, there are several proofs of this result. I'll choose probably the most algebraic proof because we will see later that it applies not only to bounded self-adjoint operators, but actually to self-adjoint elements of any C-star algebra. So let's take a point lambda in the spectrum of T. So let's write lambda in the following form: alpha plus I beta, where alpha and beta are real numbers. So what we want to do is to show that beta is 0. And let's take any real number s and observe that lambda plus Rs belongs to the spectrum of T plus IS1. Belongs to the spectrum of T plus IS1. This gives us the following inequality. The absolute value of lambda plus Is is less than or equal to the norm of T plus IS1. This is a general property of the spectrum, that is the spectral radius of each element of each bounded linear operator, or more generally of any element of a Banach algebra. Spectral radius is the supremum of the absolute values of elements in the spectrum. So the spectral radius is less than or equal to the norm. So we have this inequality. For convenience, let's take the squares here and here. And let's apply the C-star property. So by the C-star property, this is nothing but the following, the norm of the following operator. And since T is self-adjoint, the adjoint of the first operator of T plus IS1 is T minus IS1. And when we multiply these two operators, what we get is T squared plus S squared 1. So the norm of this operator can be estimated as the norm of T squared plus little s squared. On the other hand, let's look once again at the left-hand side of this inequality. Well, lambda plus IS squared. What is lambda plus IS? Lambda is alpha plus I beta. So this is alpha plus I multiplied by beta plus S. Well, and the square of the absolute value of a complex number is the square of the real part plus the square of the imaginary part. So this is alpha squared. This is alpha squared plus beta squared plus s squared plus 2 beta s. And finally, we now substitute this expression here. We can cancel s squared here from here and here. And what we get is that alpha squared plus beta squared plus 2 beta s is less than or equal to the norm of T squared. And this holds for each real number s. And clearly this is possible only if beta is 0. I'm assuming you know from your secondary school that the graph of such a function looks either like this or like this. In both cases, if beta is non-zero, then this function is not bounded from above. So the only possibility is the case where beta is 0. Okay, and this completes the proof. So the spectrum of a self-adjoint operator is real. Here's a simple corollary. If T is a self-adjoint operator on H, and if we have two eigenvectors, x and y, that correspond to lambda, to eigenvalues lambda and mu, and lambda is not equal to mu, in this case, x and y are orthogonal. X and y are orthogonal. So the eigenvectors corresponding to different eigenvalues are orthogonal to each other. And the proof is just a line. If we look at the following number, we take the inner product of x and y and multiply it by lambda. So we can move lambda from here to here and replace x by tx. And now we move t from here to here by using the assumption that t is self-adjoint. Now ty is mu y. The inner product is antilinear in the second variable, so formally I must write the complex conjugate of mu here. But we know that mu is real. because each eigenvalue belongs to the spectrum. So mu is real. And if we now compare this and this, well, since lambda is not equal to mu, this can happen only if x and y are orthogonal. And that's it. Well, okay, another useful property of self-adjoint operators, actually it holds for normal operators, is that the spectral radius is equal to the norm. If T is a normal operator on a Hilbert space H, and the spectral radius of T is equal to the norm of T. So let's recall that in the general case, we have an inequality. So the spectral radius is less than or equal to the norm. But for normal operators, they are the same. The proof is a kind of trick. We just apply the C star axiom, the C star property 2 or maybe 3 times. First of all, let's observe that actually for each bounded linear operator T from H1 to H2 between any two Hilbert spaces, the operator T star T is self-adjoint. If we take the star, if we apply the star to this expression, we get the same operator. So this operator is always self-adjoint. Well, now T is normal. Now T is normal. First of all, we apply the C star axiom to this property to S. And observe that the norm of S squared is the square of the norm of S by the C star property. And now we apply the C star property again, but now we apply it to the operator T. And we get the following equality. For convenience, I take the square of the C star property and write it in the following form. So this is true by the C star property. Then what? Well, this is S. This is our operator S, and we can apply this property. So by this observation, this is the norm of the operator T star T squared. Well, T star T squared, what is this? This is T star T T star T. But T is normal. T is normal, so we can interchange T and T star here. And we get, what we get is T squared star T squared. And finally, we apply the C star property again. Now we apply the C star property to the operator T squared. And we see that this is the square of the norm of T squared. So we see that this number is equal to this number. Квадрат спряженного. Ну, это вроде одно и то же. Мы же знаем, что ST со звездочкой, это T со звездочкой, S со звездочкой. Но в частности, если S равно T, то получается, что T в квадрате со звездочкой – это T со звездочкой в квадрате. Правда вроде, да? Okay, so now this number is equal to this one. So we'll take the square root And we conclude that the norm of t squared, the square of the norm of t is equal to the norm of t squared. So at the very beginning of the proof, we observed that this equality holds for each self-adjoint operator. Now we see that it holds for each normal operator. And now we recall, to complete the proof, we recall the general formula for the spectral radius. The spectral radius is equal to the following limit. This is true for any element in any Banach algebra. Of course, we can replace here n by powers of 2. The limit will be the same. So we take the limit over the powers of 2. But if we use this formula and we use induction on n, we easily see that this norm is nothing but the norm of t to the power 2n, 2 to the power n. This is just the induction on n. And that's it. So we see that this sequence is constant. This is just the norm of t. And this completes the proof. So if we now combine this with, so this is theorem 2. If we combine theorem 1 and theorem 2, so if we apply this to self-adjoint operators, we see that if T is a self-adjoint operator on the Hilbert space, then the spectrum of T is contained in the closed interval from minus norm of T to the norm of T. And moreover, either the right, I mean the norm of T or the minus norm of T belongs to the spectrum. Well, indeed, we know that the spectrum is real. We know that the spectrum, the spectral radius is less than or equal to the norm. So this gives the following conclusion. But now we know that the spectral radius is exactly the norm. So this implies that either this point is in the spectrum or this one is in the spectrum. Because otherwise the spectral radius would be smaller than the norm of T, which is not possible. Okay. So now we know that the spectral radius is equal to the norm. And another, maybe the final piece of information about arbitrary self-adjoint operators is about invariant subspaces. So we have the following proposition. Suppose that T is a bounded linear operator on a Hilbert space H. And suppose that H0 is a closed vector subspace of H. I claim that H0 is T invariant if and only if the orthogonal complement is invariant for the adjoint operator. H0 is T invariant if and only if the orthogonal complement is T star invariant. Well, this is more or less automatic. So H0 orthogonal is T star equivalent if and only if, so equivalently we can write this in the following way. For each y in H0 orthogonal, and for each x in H0, the inner product of t star y and x is 0. So this means that t star of y is orthogonal to x. And since this holds for each x in H0, this means that t star of y belongs to the orthogonal complement. So this property means that t star takes the orthogonal complement of H0 to itself. Well, but what is this? This is the inner product of y and t of x. And so this means that t of x is orthogonal to y. And since this holds for each x and y, each x in H0 and y in the orthogonal complement, this means exactly that t takes H0 formally to the double orthogonal complement, to the orthogonal complement of the orthogonal complement. But the double orthogonal complement of a closed vector subspace is just the same subspace. And so we see that this means that H0 is T invariant. And as a corollary, we see that if T is a self-adjoint operator, on H, then the closed vector subspace H0 is T invariant, even only if the orthogonal complement is T invariant. Okay, so that's all I wanted to tell you about arbitrary self-adjoint operators. And now let's specialize to the case where the operator is compact and self-adjoint. So we start with the following auxiliary proposition, which is also quite useful. Suppose that T is a compact self-adjoint operator on H. Then the norm of T can be calculated as follows. So roughly, this is the maximal eigenvalue. Or more exactly, this is the maximum of the absolute values of all eigenvalues of our operator. This is quite convenient if we have some concrete operator given by a concrete formula, for example, some integral operator on the L2 space. If we can explicitly calculate the eigenvalues, then we can find the norm. Just to take the maximum of the absolute values of all eigenvalues. By the way, this is closely related to one of the exercises in the sheet 2. And the proof is just a combination of our earlier results. First of all, we already know that the following inclusion holds. This was proved at the very beginning of today's lecture, and this holds for each compact operator on a Banach space. So each non-zero point in the spectrum is actually an eigenvalue. So we conclude that the spectral radius, first of all, we know that the norm is equal to the spectral radius of T. The spectral radius is the following maximum. Of course, we can consider only non-zero points here in the spectrum. And because of this inclusion, we get what we need. So now we are ready to prove the central result in the theory of compact self-adjoint operators, namely the Hilbert-Schmidt theorem. Suppose that T is a compact self-adjoint operator on a Hilbert space. Then we have the following results. First of all, I claim that there exists an most countable orthonormal family, as denoted by EI in H. So since it is at most countable, we may assume that I is, the index set I is either the natural numbers or the finite set from 1 to n, or empty. The empty set will correspond to the zero operator. Such that the following properties hold. Property 1 is that each vector in this family is an eigenvector. Is an eigenvector corresponding to a real non-zero eigenvalue. Or lambda I is real and non-zero. So this explains how T acts on the linear span and also on the closure of the linear span of this family. The orthogonal complement of this linear span is nothing but the kernel of T. The kernel of T is the orthogonal complement of this family. So these two properties together already imply that T is, in a sense, diagonalizable. So it is diagonal on the closure of the linear span of this family, and it is zero on the orthogonal complement. So this is the structure of our operator. Moreover, property 3, the set of all elements lambda I is nothing but the point spectrum minus 0. It's the set of all non-zero eigenvalues of T. Property 4, of course, I don't claim that all these eigenvalues are distinct. Some of them can appear several times in the sequence. What I want to prove is that if I take an arbitrary non-zero eigenvalue, non-zero lambda in the point spectrum, then the number of instances of this element in our sequence, that is the cardinality of those points I, such that lambda equals lambda I, is nothing but the multiplicity of this eigenvalue, and it is finite. It is finite. And property 5, if our family is strictly countable, that is, I is the set of natural numbers, then the sequence lambda I converges to 0. And maybe one more useful formula, the so-called Hilbert-Schmidt decomposition. Hilbert-Schmidt decomposition. For each element, each vector x in H, the following formula holds. T of x is the sum of the following series. Well, it's a series if the family is countable, and it's a finite sum if it is finite. Okay, so this is the Hilbert-Schmidt theorem. Well, I'm afraid we have no time today to prove it. So the proof will be given at the next lecture. And now I'll just give a few comments and some corollaries of this result. We have already observed that in some sense, if we try to write a kind of matrix of T, more exactly not of T, but of the restriction of T to the closure of the linear span of the family, let's observe that I don't claim that this is an orthonormal basis. This is just an orthonormal family. So if we restrict T to the closure of the linear span of this family, then we get this. Just a diagonal. The matrix of T with respect to this basis will be diagonal. And since it is invariant, we get kind of this picture on the whole space. In a special case where H is separable and infinite dimensional, this can be stated in a slightly different form. So first of all, let's introduce a useful notion of unitary equivalence between operators on Hilbert spaces. So suppose that we have two Hilbert spaces, H1 and H2, two Hilbert spaces. And suppose that S is a bounded linear operator on H1, and T is a bounded linear operator on H2. And also suppose that we have a unitary operator from H1 to H2. Let's denote it by U. A unitary operator. Let me recall that unitary means that it is bijective, a linear bijection, which preserves the inner product. In this situation, we say that U is a unitary equivalence between S and T. A unitary equivalence between S and T if the following diagram commutes. The diagram is more or less obvious. So this is S, which acts on H1. This is T. T acts on H2. And this is U. U is a unitary isomorphism between H1 and H2. And in this situation, if such an operator U exists, then we say that S and T are unitary equivalent. S and T are unitary equivalent. Unitary equivalent. So this is a natural equivalence relation between operators on Hilbert spaces. In some sense, S and T are the same. So formally they are different, but essentially they are the same. Well, and a corollary, which is actually a little exercise for you, but this is very easy. Suppose that H is a separable infinite-dimensional Hilbert space. A separable infinite-dimensional Hilbert space. And T is a compact self-adjoint operator on H. I claim that T is unitarily equivalent to a diagonal operator that's denoted by M alpha on the little L2 space, where little alpha is an element of C0. That is, it's a sequence converging to 0. And M alpha acts by the following simple formula. So we see that essentially each compact self-adjoint operator on such a space is a diagonal operator on the little L2 space. Okay, so that's all for today. At the next lecture, we first of all will prove the Hilbert-Schmidt theorem by using the Richauder theory. And then we come back again to Fredholm operators. First, before we come back to Fredholm operators, we briefly discuss, we make a little digression to the Banach space theory, and we discuss the notion of a complemented subspace of a Banach space. This will be essential when we study the Fredholm index. And then we come back to Fredholm operators, and by using the Richauder theory, prove some important results. First of all, we prove some important characterizations of Fredholm operators, and some nice algebraic and topological properties of the index. Okay, thank you.